Okay, today we're going to pick up at Chapter 3, Solving Nonlinear Equations. This starts with just how to manipulate nonlinear functions into a form that can be solved. Then we'll go over several, honestly, quite simplistic approaches to numerically find these zeros, which become solutions to the equations themselves. So I'll be, like I said, starting Chapter 3 in the textbook, going through and stopping at section 3.9, getting into where you start having systems of equations having multiple roots. We're not going to go into systems yet in this video. That'll be in a follow-on. But first of all, we need to discuss the different types of nonlinear functions that may exist. Some of them have no solution at all. It's possibility that the function itself, even as manipulated, never crosses zero. There's no guarantee that your aircraft can reach 14,000 miles per hour. You may not have the thrust for it. It may be a no solution set. The function may just touch barely in one point for a singular solution, and that one can actually be a very challenging solution to find, with some methods failing somewhat spectacularly. The most common would probably be these two scenarios in the right, where you either have one solution to a nonlinear equation or several solutions where you have multiple crossings of a zero in the equation form as given. So let's first look at how to translate a given nonlinear function into a form that these algorithms expect. So the example given in your text is of the form 8 equals 1/2, I believe they use radius of 3, theta minus sine theta. Oops, forgot the minus. So in that case, it's a nonlinear function, and you could certainly iterate and try to find the answer in your calculator, so on and so forth, but there's not really a way to directly solve for theta. What you can do, however, is move 8 to the other side. So if we just take this over here, subtract 8 off that side, we can make this equivalent to f of theta. That's now a function of theta alone. That's the only independent variable left. We could also represent this as 8 minus 4.5 theta minus sine theta. Just depending on which side subtracted from the other. Both equal and should produce the same zero. So in this case, you would be seeking to plot this at several different values of theta, and you want, for this to be a true solution, it has to be equal to 0. That's the reason you find all of these functions and all of these algorithms seeking a point that will result in the functions being valued at nothing. That is known as a functional root. In fact, the very function built into MATLAB for finding these 0 points are called roots. If you think about polynomials, we find the roots to determine dynamic performance in the S-plane. We want to find the system roots of aircraft and dynamic systems to figure out how they're going to behave. And that all comes back down to finding the zeros of these functions. So the methods we're going to go through today are the bisection method, the regular-Falsy method, Newton's method, secant, fixed point iteration methods, and we'll stop there before getting to systems of nonlinear equations, which really becomes a systems approach to the Newton method. So one way to solve these, it's just a brute force. This is what you might program if you had no better method. You would, not having any insight to what this function looks like, you might guess some location value. Say your first guess is x equals 1. You get a value up here quite high. Obviously not a 0, obviously not a solution. So you say, okay, I want to guess x equals 2. It'll change a little bit. And then this becomes your life. You just keep guessing values, and hopefully it's getting closer, hopefully it's getting closer. 3, 5, maybe if you got here to 7, it's actually negative. And you just iteratively improve. But that's just hunting and pecking. There is a scientific method name for this. It's called Monte Carlo, where you just throw a lot of random points around and see what ends up landing close. You just have a computer brute force calculations and a random scattering and hopefully eventually you hit a point that is close enough to be within what's known as your tolerance for the fit. That's something important to understand. For the tolerance is that close enough to zero. I didn't give you any labels. I didn't give you any distances. Who knows how close that actually might be. Do you need to be on the scale of accuracy, if this is the true solution, no numerics involved, mathematically perfect? If your numeric solution, iteration distance away from the true solution, was 1 inch, is that suitable? What close doesn't count except in horseshoes and hand grenades. That's the old adage, right? 1 inch is certainly a pretty good horseshoe throw. But perhaps if you're doing machining of high tolerance aerospace components, if you have a deviation in 1 inch away from the tolerance you want to hold, then that's actually quite terrible. Then you might not be satisfied until you're held to a tolerance of perhaps 1,000th of an inch. This type of understanding is called tolerance, just like it is in machining. It's the convergence tolerance, also known in some pieces of software as CTOL. Convergence tolerance of the solution. How close do you finally need to have the real answer to a true value of 0 before you're satisfied? Now, this does not mean, well, I guess it could be done both ways. That the answer is solving to 0, or that your estimate has now closed in within a certain range that you're satisfied with. Do you need to have it within 1,000th of an inch? Do you need to have it within 15 inches? Are you not even dealing with inches? Are you dealing with a variable that is time? It depends on your specific convergence criterion. But you need to have that in mind. If you tell the computer to go on until you find the perfect answer, until you say, my x of n minus x of n minus 1, if you want the perfect answer, that means that your next iteration didn't change at all. That means that you are perfectly 0.000 out to machine precision on the eventual solution. Now, eventually a computer can reach that out to machine precision, but then you're not really truthfully at the perfect answer. You're still just at that, 2.2 times 10 to the negative 308 minimum double floating point value representation. So you've wasted a lot of time and it's still not perfect. You could have stopped 200 orders of magnitude ago, and as far as convergence criterion, and been within the distance of atoms away from the true solution. So set a reasonable convergence criterion. Set it too wide to begin with, and then you can always add iterations later on if necessary. All right, first up is the bisection method. This is most easily understood in a graphical sense. You'll find the algorithmic progression of this is on page 61 of your text. I've highlighted the first step there. It actually skips pages over to page 62. So steps 1 through 4 actually outline the specific rote process for going through the bisection method. But we'll go step through one thing graphically here. Figure 3.7 is the textbook's graphical depiction. But we can maybe do this a bit better if accompanied with annotation. So the bisection method, as many of these are, is based on the intermediate value theorem. You want to find a point, we should start with A, not B. You find a point A and B such that they're of opposite sign in the resulting function. So this would be x1, this would be x2 as far as x values of interests. This would be functional value of x1 equals A, functional value at x2 equals B. Erase that, it's just making a mess. But that's the idea, that whenever you've evaluated the objective function, you arrive at the outputs A and B at x1 and x2. So the intermediate value theorem, of course, states that at some point that function is going to pass through 0 in the domain between those 2 points. The bisection method tells you to, bisect that domain that you know it has to pass through. Let's just check the middle. So go halfway, average the values x1 and x2, and you get x3, and you evaluate the function. If you evaluate the function and it's a negative value, then obviously you know through the intermediate value theorem that the crossing does not occur between x3 and x2. You know that now your domain of interest is between x1 and x3, so you would just repeat this process again and again, dividing that, and this would become x4, and perhaps x4 you evaluate the function that's actually above, so you can now eliminate this leftmost region. And guess what the process repeats again? You just highlight the remaining region, bisect it. Ooh, we can actually zoom all the way in. Well, maybe not all the way in. That's the most the surface will let me do. Shucks, that would have been good. But you see that that's effectively what happens. You zoom farther and farther into the function, and you can repeat this process for as long as you care to, taking a new midpoint, evaluating, doing a functional call. So you actually have to evaluate the function. Now this would be, well, we're all the way up to x5. And of course, if x5 is on the bottom, you know that you do not have a crossing in that region, and that region is eliminated. So now we know that the solution must lie between x4 and x5. Somewhere in that region, you could continue evaluating until that distance became smaller, because that's what we're concerned about. Convergence tolerance, like we said, CTOL. That would be x5 minus x4. That is the range you have confirmed the solution is down to. If that distance is less than your convergence tolerance, then you're done. You know that your latest solution, x5, is now sufficiently within the range of the actual answer. Now, the textbook's definition for tolerance is the absolute value of b minus a over 2. So absolute value, because you don't really care if it's on the right side or the left side of the tolerance, and divided by 2 is because you're assuming that the actual answer may be roughly in the middle of that domain. You have no reason to believe it's biased right or left. All you can say conclusively is that it's somewhere between. So the tolerance value is about half of that. But if you really think about what's going on here, you're most directly concerned about the uncertainty of the region that the answer could be within. So that distance, in my opinion, from between x4 and x5, or your most recently updated A and B points, is the most critical number to track. So that is the bisection method. Numerically, the way you can determine how to throw out one of these sides is actually somewhat intuitive. So if you take the functional value at A, and let me draw one of these scenarios new down here so it's a bit fresh. That last image was getting cluttered. So again, we have point A, point B. That's our initialization. We found 2 points that bisect the solution, meaning they do cross 0 and they are of opposite sign. We intentionally go halfway between the two and evaluate a point C. In fact, the textbook refers to this point as x in S1. So in this case, if you multiply together A and that new point, and the product is less than 0. So the functional evaluation of A, which will be some positive value, let's just say this is 3, and this is -2, and this was -0.5. So if you multiply together 3 times -0.5, you get, well, that would be -1.5. So if it's less than 0, then the true solution is between A and that midpoint, which we do find is actually true. The only way that product can be less than 0 is if they are of opposite sign. An opposite sign means that you've had a 0 crossing. If you found that this example was not true, if we had the alternate circumstance where this midpoint was above, let's say C equals 1, so you would have an A value of 3 times 1 equals 3. That means now that the functional value at A multiplied by the functional value at the midpoint is greater than 0, and the opposite case has to be true, that the true solution lies between C and B, somewhere in this region. So you'd actually cross out the leftmost. So both graphically and mathematically, there are ways to exclude the region that is invalid, and you're left with, well, something that works. It's a very simple method. It's very robust, meaning that it is not subject to divergence. Specifically the Newton method, although quick and powerful, in this list of processes we're going through today, this list of algorithms, the Newton method in particular is rather subject to divergence. So if you're looking for something that is robust and will work in almost every circumstance, the bisection method is great. It can take a few more iterations and functional evaluation calls than other methodologies to find their actual right answer, but hey, if you just need something to work reliably, it's the way to go. Okay, the regular-Falsey method is also a bisection method, but with a bit different way of figuring out what the next point should be. It is still called a bisection method because you have to begin with 2 points that are on opposite sides of the solution being our goal of reducing the y value to 0. Because we've rearranged the nonlinear equation to find a solution for the one variable that remains, because these are all single-dimensioned problems where the system solves to 0. You moved everything to basically just one side of the equation, so you want it to balance to nothing. So figure 3.9 in your textbook, which I'd encourage you to open up and follow along with. This would be page 64, as well as the procedure we're going to follow through, steps 1 through 4 here on the right side, page 65. Encouraging you to highlight equation 311 because that is the update equation. We'll go through and use these different components in our example. So initially what this is really doing, if I can just describe mathematically what's going on in the background, is that you're making the assumption that the straight line connecting points A and B, if I can label those, A and B, is going right between them. Of course, they'll have a 0 crossing, and that's what you're looking to estimate. Because now you will update and evaluate the function again at the 0 crossing, not at the arbitrary midpoint between A and B. You only want to now run the new functional value at the 0 crossing, which probably the first iteration will have some offset. So you would again, from that new point, we would call this one C, you would recalculate the derivative, find its 0 crossing, and run the function one more time, which, okay, you probably still have a little bit of offset, but you see how this is occurring. Eventually, the error becomes smaller and smaller and smaller until point maybe E or F or G finds something within an acceptable convergence tolerance. Again, you're not trying to find the exact perfect solution. You're just trying to find something that is close enough. So let's discuss the formula behind finding the next step. So step 1, you find a interval between points A and B such that the solution exists between them. That just means that A and B are of opposite sign. Calculate the first estimate, x in S, by following the formula in equation 311. So quite literally the value A all divided by functional evaluation at B minus the functional evaluation of A. So where A and B are your two different values of x, you found two different locations that results in the functions being opposite sign. So this is your update system. If you know the A and B you've started with, you can fill in those numbers, that's fine. Then you evaluate the function twice for FA and FB, giving you a new x location to study. So really, you could replace A and B with x1, x2, then x in S would become x3. We can use this as xi plus 1, xi plus 2. However you want to go about annotating these systems, it's just an update equation. This lets you update the estimate successively using these gradient estimates. It's possible that in the update you might actually end up flipping the interval. In the example I showed, everything ended up on the side of B every single time, but if the function ever evaluates to a positive sense, then it actually would, the interval be between your left and mid point. Again, it's not really mid, it's where it intersects the y-axis. So you again just always default to the sub-interval that contains the solution, and just like in the previous case, you evaluate the left-hand side multiplied by the new 0-point crossing to see if their sign is less than or greater than 0 to see which interval that equation falls on. So again, it's just looking at, instead of the arbitrary midpoint between two locations, if this was the true function between them, you would take the linear estimate of the derivative between the two, find the 0 crossing. This is what the formula x in s is doing. That is a rearrangement of just a linear line fit right between the two, solving for that new x location of your crossing. It's not perfect because then you have to evaluate the function again, and if that green line was our truth, that function will evaluate positively. This is an example where you would end up throwing out the right-hand side, and if I can zoom in a little bit, making a new estimate there, get the crossing, evaluate, new estimate, and you see this process just repeats until my drawing is basically just a scribble all up and over itself again. No, that would be bad. But you see that graphically, resolution has gone very quickly. You want to just monitor the change in your x-axis between iterations, and once that change is smaller than your convergence range, you stop, and you accept that as your answer. And again, just like I said previously, that selection of the proper convergence range dictates whether your code runs for a minute or for fractions of a second. Okay, third up in the list today, Newton's method. This is not a bisection method. The first two methods had different criterion for updating the bisect. This is different. It's a gradient-based update method. Of importance, this is page 66, 67 in your textbook. The update equation of importance is equation 314, and the criterion, the algorithm, is actually quite a bit shorter now. It's one of the reasons people like Newton method. It's very simple. It's just steps 1 and 2 there on page 67. But if we go back, what it is intuitively doing is you start with an arbitrary point, hopefully somewhat near the 0 crossing. Notice just 1 point. The update is defined as your next point, so I plus 1. You only know xi. This is essentially where you've guessed your initial point, xi. That particular iteration equals xi minus the functional evaluation at xi divided by the derivative of the function at xi. Now, this is not the numeric derivative. This is the actual derivative. You need to know the functional value and the derivative of that function at the location you're working with. That's one of the downsides to Newton's method, is sometimes when you're taking data, sometimes if you're looking to find a root crossing in something that was non-functional, or you never knew the algebraic function of, this isn't a feasible way to approach it. But anyway, if you take the functional value divided by the derivative, that essentially is calculating the slope of intercepts. So this is projecting a vector given that slope, and you say, okay, this crosses 0 at this new location. That will be my x of I plus 1. If we started at 1, this is now x2. And you start the process over again. You evaluate the function at x2. Look, it's still positive. Reproject the 0 crossing. Falls a bit short. Reproject until you finally work your way down to the 0 crossing location. Now this is not always going to work out. Even just graphically, we can expose some difficulties that Newton's method might have. There's a discussion on page 69 and 70. I would encourage you to read about the instability of Newton's method. But hey, we're just looking at pictures on a computer screen right now, so let's just draw one. If you had a function, and I'm going to try to draw one that is particularly prone to issues. So let's do something that looks like this. And let's guess our initial location as having struck somewhere here. So if this is x of 1, we would evaluate the function at that location. We'd also evaluate its derivative in order to calculate the tangent to that function. So we plot the tangent line and find that, oh, our next iteration should be here at x2. Already you see this is actually probably on the other side and farther away from the actual 0 crossing we are hunting. So x2, we would evaluate the function, knowing that, keep in mind, we don't have absolute and true knowledge of this green arbitrary line I drew. We might just be numerically pinging that just a few times. And the issue is the tangent line now throws us all the way. I mean, ridiculously out of form, way over here to the left. If it's almost zero, it could be off screen. But you see this is actually trending outward. If I had drawn this a bit different, we might find the crossing occurred here. Functional evaluation, we go way off to the other side. It's divergent. This is what you would view if you just called, if all you were looking at is numerical data. You might see that the first guess was 2, the next guess was 4, and then the following guess starts going to -3. The next guess might go up to 20, -50, and on a number line you need to visualize this. It says if you started here, it iterates to 4, then it gets -3, then it gets 20, then it's way off screen to the left. You're not getting better. The sequential guesses are diverging away from one another. That means their tolerance is growing. The distance between successive guesses was 2 to begin with, and you went from 4 to -3, so that's 7, and then from -3 to 20, so that's 23, and then positive 20 to -50, that's 70. The deltas between your update rates are growing instead of shrinking. You want the change to become smaller and smaller and smaller to show that the solution is stepping down towards something that is converging. Until finally you can say, okay, that step was small enough, let's halt. So properly behaved Newton's method has to be initialized within a suitable convergence range. And can I give you a criteria for that range? No, it's different for each function, it's different for each root of each function. But it might be useful for you to give multiple possible seeds. So this is a function that has one crossing. In fact, I'm going to redo this in a bit different color, same shapes, different colors. So the function is in red, the chart is just in blue. If you went in here and put several initialization seeds, whether randomized or placed at regular intervals, you would find that quite a few of them don't work. Anything captured here on the left would not work functionally. So let's say if we evaluate Newton method here, we'd find the derivative of the projection would go all the way massively over to the right. New method, projection over here to the left. Actually, that might get lucky and just out of happenstance graphically converge. Yeah, it will. Man, made up an example, first example, bad. But anyway, it can very easily lead to circumstances that maybe only 1 out of the 4 points you guess actually converge, but that's really all it takes. It's very easy to verify numerically if a solution is true or not. You just plug it into the original function, and you see if it solves to 0. If you get an answer of negative or positive infinity, then yeah, it probably didn't work out quite right for you. But you want to eventually, of course, find a solution that is converging down to this 0 crossing point. I would suggest that points 3 and points 4 in this occasion would have a high success rate of converging down to that. But if you're far away to begin with and the gradients are pointing you, especially if this was slanted down, it would actually point you away from the solution direction, and bad things could occur. So the Newton method, the important thing to remember is the update, and also that the Newton method requires knowledge of the algebraic derivative. There's a numeric equivalent to this, which we'll cover next. Similar to the Newton method, it would be nice to have a gradient-based zero search function that didn't require algebraic knowledge of what's going on in the background. So let's just figure out how we can do that. It's called the secant method because you will in the end take the secant between the segment really between two initial points x1 and x2. You do functional evaluations at each of those points. And right now that's all the knowledge you have of the function. So you would draw a line straight through them, find the zero intercept, and that is where you place your update, x3. This graphical process is represented by equation 326 in your textbook. That equation reads x of I plus 1. Your update equation equals x of I minus functional evaluation of xi, x of I minus 1 minus xi divided by functional value of xi minus 1 minus functional value of x of I. So this means, for example, let's take going after x3. To initialize this method, you have to start with 2 points because you're referencing both. If I can start circling some things, you're referencing the initial value and the value before it. I shouldn't say initial, I should say in this case, x2, and x2 minus 1 would be x1. So you need to have knowledge of 2 preceding points to estimate the third. The nice thing is, as you do this update, you've located x of I plus 1, which really, if we plug in the true subscripts, this becomes x3 equals x2 minus functional evaluation of x2, x1 minus x2 divided by functional value of x1 minus functional value of x2. So that is essentially the change in distance divided by change in height scaled by the functional value of x2, giving you the offset to locate the x location of x3. The missing point here is that you eventually will, not eventually, the next step is to evaluate the function at x3, and this whole process starts again. So all these subscripts have to be updated following the update equation, and again that equation is in your textbook 326. You'll update the equation, and now instead of plotting the secant between x1 and x2, you would redraw it between x2 and x3 to find the crossing point where you would place x4. Do your functional evaluation, and perhaps, depending on what your function is, it might be negative now. So then x4 and x3, something interesting has happened at this point. You're crossing 0 between the 2 locations. But still, using the same update equation, it will find and project its path right down to the x-axis. So x5 is in that location, and you keep going through the same process to arrive at the eventual solution. So that same update equation and methodology of really just projecting the slope down to the x-axis crossing works. Will this work every time? No, it's still subject to the same misguided gradients that can capture the Newton method. This doesn't, however, depend on any knowledge of the derivative of the function because you are in truth numerically approximating the derivative across a larger step size. It's fairly robust. Like I said, it's subject to the same caveats as Newton method, but really something I like doing. I always, most always, in a numeric sense, use this over Newton's method by default. And now for the last in our list of nonlinear solution functions, at least for those of a single dimension, is fixed point iteration. Everything we've been doing so far has put the function in the form f of x, that's our nonlinear function, equals 0. So you move all the components over to one side. You want to find the root, which corresponds to a functional evaluation of 0. When everything is in balance in the equation, you've essentially found the solution to the nonlinear setup. Fixed point iteration is different. It says, forget that idea. Let's actually focus on an equation which they don't call f, they call g of x, just for the sake of changing the letter for clarity, equals x. So instead of solving for 0, let's solve for x. You still have plenty of other x variables on the left-hand side. You don't have to solve for the solution because, well, that is the very thing we can't do. They're nonlinear. You can't separate this out and say x equals blah, 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 y. It's not an independent function. So you have to reevaluate the function a little bit. So we'll be following their example on page 76, and the example equation given, if I can clean things up a bit, is x e to the 0.5x plus 1.2x minus 5 equals 0. So obviously this would be fine if you wanted to have just a function of y equals 0. This is already solved for 0. You can look for the value of x that eventually finds a root, meaning that the entire function is evaluated at 0. But that's not how the fixed point system works. You have several options on how to put this into an interesting formula g of x to serve as your update equation. Very quickly, you can divide this in a few different ways. The first one of which is just to move 5 over to the right-hand side. Let's clip some room. It equals 5. You'd actually probably end up taking this whole element over to the right-hand side minus x e to the 0.5 x, and of course then you just divide by 1.2, and that is equivalent to case A, equation 332 in your textbook. That's one way to rearrange the equation. You have options though. There are 3 different x values on the left-hand side, and you can actually put it in 3 different forms. The second form could be written equivalently 5 divided by e to the 0.5 x plus 1.2, and the third option could be written as 5 minus 1.2 x divided by e to the 0.5 x. So those are the 3 different options. Now, which one is best? There is actually a best option, and that is covered in the essential box 330 of your textbook. This is called the Lipschitz continuous condition, that you want the derivative of this function, so g prime of x, to be less than 1. So you actually have to go through and evaluate the numeric derivative at the point you're going to be taking this, or at the 2 points you're going to be considering in the neighborhood of the solution. So in your textbook, they actually go through and find the derivative at g prime of 1 and a g prime value of 2 for each one of these cases 1, 2, and 3. So at 1, well, we'll just write this fully out. G prime at 1 for the first case is equal to negative 2.0609. G prime at x equals 2 is equivalent to negative 4.5305. For the second case, we get negative 0.5079, negative 0.4426, and for the third case, we'll just say ditto. For the third case, you get negative 1.8802, and for the fourth, you get negative 0.9197. So to satisfy the condition that the derivative should be less than 1 for this method to achieve convergence, there's really only one functional rearrangement that satisfies that, and that is functional rearrangement 2. So this means that really that function becomes your update equation. If you plug in an initial guess, then the left-hand side essentially becomes your x of I plus 1 update equation, where all the x's on the right-hand side would just be x of I. In fact, in that case, there's just 1. So to see this progression, we'll go straight from the textbook up here in the top right component, and you see that they've begun with an initial guess of x equals 1. They plug in 1 for this first evaluation, seeing that it's an update equation, so x of 2 equals all this plugged in at 1, you get a value of 1.7552. You just repeat that equation, which numerically is easy. You just start a loop. and the loop feeds itself, checking at the end of the loop to see if you've satisfied the convergence criterion for change between 1 and, in this case, the new value of 1.7552. So the change would be 0.7552, which is still quite a bit considering the magnitude of answers we're looking for. So they plug it in again, get an updated value of 1.3869. Still a change of, what is that, about 0.35? Again, and again, and again, and again. You see it's convergent because the change in the value is slowing down. You're approaching one of the root values, and it's working. If you use one of the other formulations, you'll see that it's actually the exact opposite. This is, I believe they started using case A. So that would be the derivatives being a -2 and a -4.5. We expect this to be divergent, and it is. The update for x2 is 2.79, x3 is -5.23, and look, it's just skipping on opposite sides away from the solution. The magnitude between updates is growing. That's a divergent numerical method. So is this fixed point iteration method a problem? Yeah, I kind of think so. It's probably not worth it. You have to do algebraic manipulation and numerics perspective. I kind of am a fan of bisection. There is one numerical method where actually do order of magnitude search. There's almost a power search, where it's probably one of the most robust methods. Probably not the most efficient, but it will find a zero or multiple zeros in a domain. We'll probably show that through example in MATLAB instead of just through a written description of these algorithms in a textbook. But chapter 3, that's section 1 through section 9. You see, we basically discussed the families of gradient search-based nonlinear solutions. We've done bisection-based nonlinear solutions. And lastly, we did a different formulation going after fixed point iteration of a solution where you're seeking towards an x equals g of x type solution format instead of an f of x equals 0 solution format. So now you have actually 5 distinctly different tools, each with their own advantages and disadvantages, programming complexity and programming simplicity, to go after the solutions to nonlinear roots with.